Hey, what's up, developers? Stefan here from Be a Python Dev, and today we're going to talk about different traversals for nonlinear data structures. The first problem here is a binary tree in-order traversal. So an in-order traversal, you apparently look at any left children, then you look at the node itself, then you look at any right children. And if the left child has another left child, then you go kind of bottom up from that. But if it has a right, you just go to the right node after adding the node itself into your response. So to do this, we're going to need a return object. So we're going to declare a variable here to return. We're just going to assign this an empty list. Then we're going to create a method that we can call internally and recursively that will actually do the traversal. So we'll just call it do traverse. And this is just going to accept a node, and it's going to do some stuff. And where you need to call this function with the node itself, if there is a node. So if root, because this function could potentially be called with a none variable. So we will actually do traverse the root. And then at the very end of this, we'll return our toReturnArray. Now for the logic in the do traverse, since we want to explore the left first, if it exists, so if node.left, do traverse left. And then, like we said, we look at the left first, if there is a left. Then we look at the node itself. So this will be looking at the node itself and adding this to our response data structure. So to return node.value, as you can see at the top here, there's a definition of our tree node where it has a left child and a right child, making it a binary tree. Whereas a regular tree could have any number of nodes. This one's just going to have 2. So that's going to be kind of hard-coded to left and right, and then the value itself of the current node. So after we've looked at the left node, we're going to add the node itself, and then if there is a right node, if node.right, I actually have an error here, do traverse node.right. And here we actually need to do node.left. Okay. So what this is going to do, like in our example here where we have 1, 2, 3, there is no left child on 1, so we're going to add 1 to the output itself. We're going to look at 2, and we're going to see that 2 does have a left child, so we're going to explore the left child first. It has no other children, so we're going to add that into our return variable, our return list. And then we're going to go back to the parent root, or the parent node, and add that value. So with this tree, we end up with the output 1, 3, 2. Now our depth first search here, well, it's not really a depth first, it's a in-order traversal. But our recursive function here is going to do something similar. We're going to look at the left first, we're going to add the original value, and then we'll explore any right children on our node. So we'll just go ahead and run this code. And list object is not callable. So I forgot that this should actually be toReturn.append. So this is just a Python's internal method on the list that we declared here. This is in a top level scope that is reachable by this function, since this function is declared in the scope of in-order traversal. So we can go ahead and append to this list from within this function. That saves us from having to tote around an extra response list in the data object here itself, and potentially reduce a little bit of the memory from the recursive calls that get put onto the heap. So run this code, and you can see the input 1 null 2 3, output 1 3 2. So we'll go ahead and test this on all the test cases that LeetCode has for us. You can also define them yourself if you kind of understand how this structure works, which actually I don't, because I thought there would be a none here, but apparently there's not. Anyways, we'll just run this code as it is, and we can see that this gets accepted. faster than, that doesn't matter. Okay, so now we'll talk about another kind of traversal that you can do on a binary tree, and that is a postorder traversal. And that's kind of like a bottom-up approach. You look at the left, and then you look at the right, and if any of those have any children, you look at those first, and then you populate your response bottom up. So here in the same example that we had previously, where you have 1, 2, and 3, where you have a right node, which is 2, and then a left node, which is 3, this will get added bottom up from left to right. There is no left node for our root here, so nothing gets added there, and instead we just go, you know, pretty standard here. There's no like actual complicated example here that lets you know if it's left to right, but in general, the post order is. This is different from linear data structures in the sense like lists and arrays. When you have a list, you can only go in one direction. So you're always going to go from the parent to any attaching list on it. But with a nonlinear data structure, such as a tree or a graph, there's multiple different ways where you can traverse it. The in order, the post order, just like a standard breadth first, where you populate from left to right. And in this example, the post order, you know, that's kind of like bottom up, left to right. So let's go ahead and write this logic. It's going to look very similar to what we just wrote, where we have a toReturn equals an empty list. We will have a function call within this that we will call recursively, and we'll call this still the same thing, do traverse. But maybe to be a little more clear, we could say do post traverse. And since I don't feel like typing that much, we'll just call it do traverse, since it's inside a post order traversal named function. So I feel like that's a pretty clear variable name. We'll do the node here. And since we want to do bottom up, so we're going to explore any nodes first and then add our value. Whereas before we explored the left, added the value, and then explored the right. So this will just be a slight variation of that. If node.left. Yeah, so this doesn't actually auto-populate our method names. So I think I'm fine having it being a little bit shorter. If node.right. Basically, this is just saying if there's a node there and it's not a none value, then go ahead and do the logic within it. And then we will append the value itself. Since we know there's always going to be a value if we're in this piece of the code, it's, you know, we don't need to do any checks here. We can just toReturn.append node.val. And then if root do traverse, and we're going to call this initially with the root node itself, and then return to return. We'll go ahead and run this and see if I messed up anywhere. So as you can see, the input 1 null 2 3, and then the bottom up output 3 2 1. So we'll go ahead and submit this. Seems pretty standard. Success here in the top left corner, so we know we did everything right. And then we'll talk about a similar post order traversal, but it's a little bit complicated in that it's a N-ary tree and not just a binary tree, meaning that the nodes contain a list of children instead of just a left and just a right, which makes it, you know, slightly more complicated in the sense that you have to deal with multiple children instead of just looking at a left value and looking at a right value. You can see here 1 3 2 4, and then there's some children 5 6. So with the bottom up expectation from left to right, you would look 5 6 3 2 4 and then 1. So you can see that right here that I just highlighted in the bottom left corner. So this logic again will be very similar to what we wrote for the binary tree post order traversal, but it'll be a little bit different because we have to deal with multiple children instead of just 2 nodes. So we'll create a response object, initialize that to be an empty list. We will create a recursive function call within our function. So same thing, do traverse. Very kind of common design patterns here with different nonlinear data structure traversals, and this will just receive a node. And then what's the logic for this? If children, or is there always going to be children? There might not be children. So if node.children, and then for this, we'll just use a simple for loop iteration to loop on for child in node.children. Are these children ever actually just going to be null? They might be. So for child in node.children to traverse and then the child object that is referenced in our for loop here. So we explore any branches and then we append the node itself. I think if there's none values there, it's just going to call if node.children. Well, there's not going to be. I don't know if we need to check if node is null or not, or none. Anyways, we can check that in our test case once we actually run the editor to kind of validate our assumptions. Our assumptions is that it's not going to matter, but it might. So here you can do if child. So if the child's not none, then call to traverse, and I think we can just check that there. And you can't call node.children on a none object because that's not going to work. So we're going to need to check if the root is not none as well. I don't know why I keep typing a print. I think my fingers keep slipping. Or I should say shifting. So we'll put the value in the current node that we're looking at after we explore any children, kind of bottom up recursively. And then here, if root is not none, go ahead and do the traversal. And then we should just be able to return our return object that we initialized here. And I think this will work. So this is the same structure defined in our example case. So 1, 3, 2, 4, 5, 6 is the input, and then the output is the bottom up children from left to right. And this should work. Thousands of nodes, kind of simple post order for an N-ary tree. Go ahead and submit this. We can see that it was successful. And I hope this was helpful in kind of thinking about traversal methods of nonlinear data structures and kind of a simple a simple explanation, given that I'm just doing this impromptu off the top of my head, on dealing with the nodes, if the node children exist, and kind of defining a recursive function and doing that in a depth-first manner with various traversals. So thanks for checking out this video. Definitely subscribe it to me if you've learned anything, and catch you guys next time. Bye.